if we're going to talk about whether redox reactions occur, about whether or not there has been a change in oxidation number, then we need to be able to pretty effortlessly assign oxidation numbers to compounds, to be able to look at the atoms sitting inside a molecule or an ion and say, oh, the oxidation number is +7, or oh, the oxidation number is -2. Well, that means then that we need to come up with what the rules are that are associated with assigning oxidation numbers. These rules are typically taught to you in a high school chemistry course, but I repeat them here for you fairly quickly so that you have them in your brain and you can start doing them just like that. The first rule, of course, is what we've seen before, that free elements have an oxidation number of 0. So these are elements that have no other atoms other than a single monatomic species. So oxygen in O2, or fluorine in F2, phosphorus P4, sulfur S8, any of these compounds, because the overall compound has only a single atom in it, the oxidation number has to be 0. Now, after we get past all of the elements which are monatomic in the compounds they form, the next step is the one that borrows from what we learned when we were studying Lewis dot structures, and we understood the need to achieve a noble gas-like configuration. What we learned when we were doing those kinds of problems was very simply that if I looked at the periodic table, everything wanted to be like this. Everything wanted to achieve an argon or a neon-like configuration. So over here, elements like lithium and sodium and potassium, they all wanted to lose an electron. And if you lose an electron, you've lost a negative charge, so you're +1 overall. In this particular column here, things like calcium or magnesium had to lose 2 electrons. On the opposite side, things like fluorine and chlorine wanted to gain an electron. That was -1. Oxygen, sulfur, that would want to gain an electron. That's 2 electrons. That's -2. Sitting over here next to them are nitrogen and phosphorus. They wanted to gain 3. The other case that we worried about was this one here with something like aluminum. And it would want to lose 3. So that's how we assigned oxidation numbers based upon what particular group you were in. All the alkali metals were +1. All the alkali earths were +2. The halogens were -1, and so on. So the second, and certainly the most important rule, the one you use the most, is the rule associated with assigning oxidation numbers by groups. Now, having said that, there comes a point where as you were doing problems, assigning oxidation numbers, you suddenly are conflicted. Not always, but sometimes. If I showed you a water, for example, and I asked you to assign oxidation numbers here, you would say, well, that one's a -2, and that's a +1. That makes everybody happy, you notice, because I can set up this nice little equation that says the overall charge on the molecule or ion, 0 in this case, is equal to, and then there's this number of coefficients times the oxidation number that you add together for all of the different atoms to see if that equals 0. So let's see, if I've got an oxygen right here, this is my oxygen case here, and these are my hydrogens. The oxygen, there's one of them, and it has a -2 charge. The hydrogen has 2 hydrogens, and it has a +1 charge. What do you know? It all adds up perfectly. 2 times +1, 1 times -2, it all adds to 0. Check, everyone's happy. When that occurs, everybody's very pleased because it means everybody has gotten to do what they want to do just fine. The problem is that not all compounds work this way. Let's take something like H2O2 or something like NaO. Now, in this particular case here, these are both neutral, so I have to have them all add up to 0. And there's 2 atoms in both cases, 2 types of atoms. So I've got to multiply together the atoms times their oxidation number. Let's go ahead and do this top one here. There are 2 oxygens, and it wants to be -2. there are 2 hydrogens and they want to be +1. Down here we've got 1 oxygen and it wants to be -2, 1 sodium and it wants to be +1. When I do this, guess what? 2 plus -4 does not equal 0. 1 plus -2 does not equal 0. Evidently, my simple little Rule 1 and Rule 2 about assigning oxidation numbers isn't going to work here. So I need to have a hierarchy for the assigning of the oxidation numbers that says if there's ever a conflict between elements and trying to assign based upon rule number 1 about the actual charge associated with the group, whenever there's that kind of conflict, there has to be a hierarchy. Something's always going to win. Something's always going to come in second place. And here are what the rules are. So when I've got alkali metals, they are always +1. Always +1 unless they're in the elemental form. So when I had sodium and oxygen together, sodium got to win. It got to be +1 and oxygen had to conform. So when I was looking at that particular problem, with sodium oxide, I didn't get to call oxygen -2. What got to rule the roost was sodium being +1, so the oxygen had to be -1, and then it did work. Let's try this case here. Hydrogen is always +1, except for when it's around sodium, and therefore, if it's around something like hydrogen peroxide, it gets to be +1, and once again, the oxygen comes in second place. And so now, by oxygen being -1, I have been able to make my equality hold. So generally speaking, there's this sort of hierarchy that we establish that works this way. Things like sodium always win over hydrogen, and things like hydrogen always win over things like oxygen. This one always gets to be +1. This one always gets to be +1 except when it's around sodium. This one always gets to be -2 except when it's around hydrogen or it's around sodium. So let's look at Na2H, something weird like that. There's Na2H. I don't really know a whole lot about this compound. All I know is that it's neutral, and it involves a couple of different atoms. So there are 2 sodiums and there is 1 hydrogen. This one has to be +1, so whether I like it or not, I've been forced to make hydrogen -2 because of this hierarchy I have. So as long as you keep this hierarchy in mind, you're going to be in good shape. Now there's one other rule that you need to be aware of, and it's the rule associated with what I call everything else. When I've gone and created a periodic table here where I'm taking care of my main group guys, so I'm taking care of these guys right here, I'm taking care of these guys over here, everything else is pretty much up for grabs. Everything else, from the transition metals all the way over to even dealing with things like carbon and nitrogen, those have a highly variable possible oxidation number. So let me show you some compounds to give you a sense of this. Here's some NH3, here's some NO3 minus, here's some Cr2O7 double minus, here's some KMnO4. There we go. 4 examples of an effort to assign oxidation number to these particular compounds here. The nice thing about assigning oxidation numbers to these compounds is that it becomes really very much a rote sort of process. I would imagine that I'm going to know what K is and O is and O and O and H, that I've got those numbers assigned based upon rules that I established earlier. The things I'm not going to know about are these more exotic species, the nitrogen, the chromium, and the manganese. That, in fact, it turns out those can be quite variable in terms of their oxidation number. And so I need to follow the following guidelines. The first thing I'm going to do is I'm going to set up these equalities here. And I'm going to set these equalities up so that the overall charge of the compound sits on the right-hand side. This is overall 0. This one's overall minus 1. This is overall minus 2. And this is overall 0. Now what goes on the left-hand side is going to be this multiplication together of the oxidation number and the number of atoms for however many there are. So there are 2 kinds of atoms in this first case, 2 kinds in this second case, 2 kinds in this third case, and 3 kinds in this fourth case. And now I just stick the numbers in that I know of and solve for what I don't know. In this top case here, I know that there's 1 nitrogen, and I know that there are 3 hydrogens, and I know that hydrogen, except when it's around oxygen or sodium, gets to be plus 1. Nitrogen, I don't know it, but notice that because I know everything else, that's plus 3, that's a 1 there. The answer is that this hydrogen must be minus 3 for its oxidation number. Let's try this case here with nitrate. Notice I've got 1 nitrogen and I've got 3 oxygens. The oxygens get to be minus 2, except around hydrogen and sodium. That means that this right here, this unknown value, is what my nitrogen is. And it is, if it has to add to minus 1, it must be plus 5. Because plus 5 plus 3 times minus 2 equals minus 1. So my nitrogen here is plus 5 for its oxidation number. Look at that. My nitrogen has gone from minus 3 to plus 5. This suggests a huge change, an 8 electron change in the number of electrons. By the way, notice that this is associated with some pretty important chemical processes. Ammonia here is a source of fertilizer, right? And nitrate is this kind of waste product that does pretty much not a whole lot for us. It's associated with smog and that kind of thing. But the process of getting from this fertilizer to this smog-like substance right here releases an enormous amount of energy, and that energy release is associated with an 8 electron flow. Our ability to monitor that 8 electron flow is what electrochemistry is all about. Now down here are some other more exotic species. You may not even know what this thing is. It's called dichromate. This is called potassium permanganate. But what you do need to know is what the oxidation numbers are for the chromium and the manganese. Because if you know what they are, then you can know whether a redox process has taken place when you look at it inside a chemical reaction. So I've got 2 chromiums. I've got 7 oxygens, which are minus 2. Put the numbers in here. That's minus 14. That must make this plus 6. Because 12 plus minus 14 is minus 2. So my chromiums each have a plus 6 value here. Down here is permanganate. So I've got potassium, and there's 2 of them, and they must be a plus 1, because potassium's always plus 1. There's my oxygen. There's 4 of them, and they're a minus 2. Now you might be asking, why is it getting to be minus 2 if it's around the potassium? And the answer is, if I've got something else that I can unload the burden of fixing the number of electrons in the oxidation number on, that's what gets the burden. That's the manganese here that has to make that accommodation. So at this point, I've got plus 2 overall here. I've got minus 8 overall there. What are the numbers that I have to add up here to get the end result that I have? And the answer is, plus 6. Because plus 2 plus 1 times plus 6 plus minus 8 is in fact equal to 0. So the manganese also has a plus 6 oxidation number. This is how you assign oxidation numbers. And you might think, yuck, I don't want to be doing this. But the nice thing is that after a while, being able to assign oxidation numbers doesn't require you to do this. You can look at chemical compounds and do this kind of math in your head. What it allows you to do, though, is the very next step, the step of being able to assign and balance chemical reactions that involve oxidation and reduction. And once you've been able to do that, you can talk about whether or not you have a process which is electrochemical in nature or not. Remember, what we're getting back to, when all of this is said and done, is am I able to monitor whether electrons are moving, whether electrons in fact can fall down a hill? Well, if those electrons don't move, I'm not doing electrochemistry. Those electrons are not moving in a sodium chloride dissociation. Those electrons are not moving in an acid-base reaction. Those electrons are not moving when I'm having a physical process take place. It is only in processes in which I have a change in the number of electrons happening that will occur. And I can only know if there's a change in the number of electrons by figuring out the oxidation numbers and then taking a look at a chemical reaction like this one right here and saying, wow, it started as +1 and ended as 0. So evidently, this is an electrochemical process. This is something where I can measure the energy associated with that electron movement.